This lesson is about inverse functions. How can we reverse a correspondence given by a function f? For example, if we start with number 3 and double it, so our function is really multiplying by 2 times 3 in this case, then we end up with 6. To reverse the operation, what we really need to do is to take half of 6 to go back to 3. So if our function will be 1/2 times x, in this case 6, we end up with 3. So taking 1/2 of x reverses the action of a function f that doubles the x. And this fact can be seen if we compose the two functions. If first we apply f and then apply g, then the overall composition should not change the original x. That means this composition should really end up to be identity, starting with x and leaving the x unchanged. So these two functions are examples of inverse functions. They reverse its own process. Similarly, if we have a function that cubes an input, that to reverse this process it's enough to take cubic root. So the composition taking cubic root of x cubed, the cubic root cancels the cube, and we end up with just x. Again, we end up with identity. Therefore, these two functions, x cubed and cubic root, are inverses to each other. Well, look at one more example. Let's say if we have a function x squared, then the natural choice to reverse this operation would be to take square root. However, we have a problem here because we can take square root only of the positive or 0, that means non-negative numbers. So yes, we can reverse this process of squaring something by taking square root, but only for non-negative x values. So that's important to restrict the domain, so the composition will be actually doable. And let's check again. The composition g of f is taking square root of x squared, but as we remember, square root of x squared is actually absolute value of x, not x by itself, which means the absolute value states that it's either x for positive x's, or 0, or opposite to x for negative x's. Since we restrict our domain to non-negative values, which means this branch, therefore, our composition for non-negative values is actually just x, and yes, that means that the composition end up to be identity. However, that works only for non-negative x values, for x bigger equals 0. Let's observe some properties of graphs of inverse functions. How to recognize that two given graphs are actually graphs of inverse functions, or possibly inverse relations. Let's see the first pair of functions, the f of x, which is 2x, and g of x, which is 1/2 x. Well, that's the 2x, that's 1/2 x. So this is f of x, which is 2x, and that one is g of x equals 1/2 x. As we saw before, these two functions are inverses to each other. Let's see the second pair. We start with x cubed. That's x cubed, and the inverse is cubic root. So this is our f equals x cubed, and g function, which was cubic root of x. Again, inverses to each other. So they are very symmetrical. As you see, they are very symmetrical, kind of about diagonal, isn't it? Let's see the third example, the x squared and the square root. Well, since we are taking x squared only for non-negative values, so we're going to graph only half of this parabola. This one is x squared, half of it. The other half would go approximately like this. But to have an inverse, we can take only this particular half and reverse it to the square root of x here. So f of x was x squared, and g of x, it was a square root of x. But we had to restrict the domain to only non-negative values. So observe all three of those pairs of inverse functions, and you can probably notice that each of these pairs is exactly symmetrical in respect to the diagonal y equals x. So that's the axis of symmetry for the two graphs. Formally, a function g is called an inverse of a given function f, inverse function, and it's denoted f to the minus 1 if it does reverse the correspondence given by the function f. So, for example, if I have a domain for f and I pick a point, any point from the domain of f, and I transport it to f of x to the range, then the g function should bring the f of x back to the place of x, not anywhere else, but exactly to x. So it reverses whatever f done to the x, bring it back to the same position. And the usual notation for the inverse function is f to the negative 1. Looking at this diagram, we talked about bringing the x through the f to f of x, and then through the g, which should be in inverse, back to the x. But this composition works both ways. We don't have to start with f. We can start with g. So starting with a point y in the range of f, if we apply g first and then f, this composition also should bring f of x, or our y, to the same point y. Therefore, this really means that a g function is an inverse to f if and only if both g composed with f is identity and also f composed with g is an identity. Can every function be reversed? We already saw the example with x squared that we couldn't reverse because square root can't be applied on negative numbers. So no, not every function can be reversed. Which functions can be reversed then? Well, let's analyze the situation. If we have a function f that transports x into the y, and if this function has an inverse f to the negative 1, then this f to the negative 1 must be a function. So, for every y, we must be able to determine a unique x value such that the function f to the minus 1 of y gives you back our x. And the key word here is it must be a unique value x, because we want the inverse, which is f to the minus 1, also to be a function. Therefore, its graph has to satisfy vertical line test. But vertical line test for f to the minus 1 really means the same as horizontal line test applied to the graph of function of f, because remember, the two functions are symmetrical in the diagonal. So if we have the diagonal in the system of coordinates, the vertical line test for one function is the same as the horizontal line test for the other function, because these two lines are images of itself in symmetry in the diagonal y equals x. So we can put together our findings about when f is invertible. Well, it is invertible if and only if one of the following conditions apply. The function f satisfies horizontal line test, like we talk about here, which means that any horizontal line intersects the graph of f in at most one point. So, f is invertible if and only if f satisfies not only vertical line test because that makes it just a function, but also horizontal line test that makes it invertible. This condition is actually equivalent to saying that function f is a one-to-one function. That means that for every x, I have exactly one output y, exactly one y, and also for every y, I have exactly one input x. That means I can't have a situation like this, where the value y can be obtained for two different x's. That's not allowed. Okay, that's why we have this horizontal line test, not only vertical line test, but also horizontal. It must be one-to-one. That means for every x, exactly one y, for every y, exactly one x. Okay, so this definition of function being one-to-one, sometimes it's just denoted one-to-one like that, rather than using words. This statement is equivalent to say that if I choose two different points A and B, then the values of my function at A and B will also be different. And this happens for every choice of A and B from the domain. On the diagram, in the case of parabola, I don't have this luxury because, for example, this x and that x produces the same value. So that doesn't make it one-to-one. Okay, that's great, but maybe we don't like to use statement with not equal. Sometimes it's easier to use statements with being equal. So this statement can be reworded equivalently in the following way. If the two values of the function are equal, then the inputs for those values are also equal. So it goes backwards. If the values are equal, then the inputs must be equal. We can't have two the same values for two different inputs. That's the idea. So this statement is very useful to show that a function is one-to-one algebraically. Now let's look again at properties of inverse functions. First of all, as we noticed before, the inverse functions are symmetric in respect to the diagonal y equals x. Secondly, because of the symmetry, if a point AB belongs to the graph F, for example, on this particular diagram, this point has coordinates 3, 6, then the point with reversed coordinates 6, 3 will also belong to the inverse function. So 6, 3 is here, that's our 3, 6, 3. So if a point 3, 6 belongs to F, then a point 6, 3 belongs to F to the minus 1. They are positioned exactly symmetrically on the two sides of the diagonal. So these two distances of points from the line L from the diagonal are exactly the same. And you can see some other points, like these two, and this pair, and also that pair. Well, that tells us how to graph an inverse function. If we have graph of one function, to graph the inverse functions enough to pick the important points and transport them in symmetry in the diagonal y equals x, and then connect those images. Another observation, any monotonic means always increasing or always decreasing function. Any monotonic function is one-to-one. So it has an inverse function because a one-to-one function has an inverse. So any function of this type, always rising, will have an inverse function. Also a function that is always falling down, no matter how, but it's always falling down. Then it will be reversible. And here, more formally, if a function f moves the domain D into range R, and a function g is set up on R back to D, the function g is the inverse of f if and only if the composition g composed with f brings the x onto x for every x from the domain of f, and also the composition the other way around, f composed with g, brings the y onto the y for every y from the set of range. It happens that the inverse function is unique. So we have these two diagrams as I mentioned before. X can be transported by f to f of x and then go back by g to the x. And that happens for every single x from the domain. Also, if I start with g from any point of the range, transport it to g of y, and apply f brings it back to the y. Okay, what we already said, it means that the domain of the inverse of f is the same as range of f. Since f brings all the points of its domain to the range, and g is defined on points of the range, then the domain of g, which is the same as f to the minus 1, is the same as range of f. So R is a range of f, but it's also domain for g. Similarly, the domain of f, which is our D, becomes range for g because all the points from the red region will go onto the blue set D. So this is quite useful because, as you know, it's a lot easier to find domain of a function than the range of some other function. So this property of inverse functions we'll use when trying to find ranges of some functions. We can find out an inverse function and find its domain. That will be the same as the range of the original function. So let's exercise a bit. We need to graph the inverse relation for the given graph and state if this inverse is a function or not. So the first graph, it's a relation, that's a blue circle. To find the inverse relation, we basically need to flip each point of this graph in respect to the diagonal y equals x. But since a circle with the center at 0, 0 is actually symmetrical about any line going through the center, that means it's also symmetrical about this diagonal. That means the circle goes onto the same circle. So in this case, both relations are exactly the same. The circle of center 0, 0 is inverse to itself. Is that a function? Obviously it's not a function because it doesn't satisfy vertical line test, so not a function. Okay, try another shape, this blue curve. Well, it looks like it's increasing all the time, so it's monotonic. Therefore, it should have an inverse, and the inverse should be a function. Let's see. Let's transport every single point. This is nearly 2, so diagonally it will be nearly 2 on x. This point is stationary because it's a point 3, 3, so it goes on to 3, 3. That point on x, which is a little bit more than -4, will be transported on a little bit more than -4 on the y-axis, somewhere here. And maybe a couple more points. This point is like -3, nearly 1.5. So it will be 1.5, -3. It will be transported here, right? And then we can volunteer a shape somehow like this. It's not really vertical because this is not a horizontal. It's still increasing, just hard to draw. But it's increasing like this, right? And maybe somehow like this. So that's the approximation of the inverse function. And yes, this is a function. And the last example, this is parabola. We can flip it over the diagonal. Here's our diagonal. So the 0, 0 will be the same. The 1, 1 will be the same. But the 2, 4 becomes 4, 2. So this point is here. That's 2. And also -2, 4 becomes 4, -2. So if you connect all these points, the graph will look like that. It is an inverse, but inverse relation to the blue graph. So it's not a function. Just a relation. Since we are really interested in functions, that's why we need to restrict the domain to only half of parabola. And it doesn't have to be positive. It could be a negative half. So, for example, if I want to reverse just this part of the blue graph, then it will become that part of the red graph after the symmetry in the diagonal. Okay, in this example, we are asked to find the inverse function of 2. That means how much is f to the -1 of 2, knowing that f of 5 is 2. So if I start with 5 and function f brings the 5 to 2, then function f to the -1 takes the 2 and brings it back to 5. So the answer is very simple. F to the -1 of 2 is actually 5. Okay, how can we determine if two given functions are inverses to each other without actually graphing them? Well, in the first example, we have given two functions as a list of ordered pairs, and it's not too many of them, so it's very easy to check. G can't be an inverse of f, because f moves 5 to 7. Therefore, I would expect that G would have 7 in its domain. The range of f should be domain of G, but it isn't. So the point 7, 5 doesn't belong to the G function. Therefore, G is not an inverse of f. It's not the same as f to the minus 1. Even though the first 2 points are really reversed, because we have a pair -3, 6, and yes, we have a pair 6, -3 in the g function. The same is with 2 and 1 and 1 and 2. That's okay, but the last point makes it not possible, so these two functions are not inverses. If we'll reject the last point, if we change the f, then such modified functions would be inverses. Okay, but how to find if the two functions are inverses if we have given two formulas? Well, we need to follow the definition of inverse functions, which states that the composition of f and g must be identity, and also g with f must be identity. So those are the two conditions that we need to check. Okay, let's check the first one, f composed with g of x. We need to calculate this composition. So f applied on g. F follows the rule 1 over the input. The input will be g of x plus 1. So what we really have is 1 over 1 minus x over x plus 1. And here we deal with complex fraction, but we know how to simplify complex fractions. We can multiply the top and the bottom by common denominator, which is x. And then we end up with x over, this x will cancel that x, so it will be 1 minus x, and x times 1 is plus another x. Okay, that's good because we can cancel the x's. And yes, indeed, we end up with just single x. X over 1 is x. So the first condition is satisfied. Great. Well, that's not the end. We also need to check the other composition, g composed with f of x. How does this work? Well, we follow the g function, which is 1 minus the input f of x over f of x. Now we plug it in what f of x is. It's 1 minus 1 over x plus 1. So it's some work with complex fractions. X plus 1 equals, we're multiplying the top and the bottom by x plus 1. So the bracket times 1 is just x plus 1. Then the bracket times the fraction, that will cancel each other. So you end up with just 1 over, and here they will cancel each other, so you end up with 1. 1 cancels as well, so yes, we end up with x. Second equation is checked. Therefore, we can claim that yes, f and g are inverses to each other. In the next example, we want to determine the domain and range of the two functions in the previous example, in tray B. That means these two functions f and g. Then we need to give equations of horizontal and vertical asymptotes for each of the above functions. Let's start with domain of f and g. We know that domain of f is all real numbers except for the ones that will make denominator 0. So it's all real numbers but not -1. Since both functions are inverses to each other, we know that domain of f is the same as range of g. Similarly, if we start with domain of g, which is all real numbers except for the ones that make denominator 0, so it's all real numbers but not 0. And since they are inverses to each other, this is the same as range of f. So we already have the domain and range of both functions. Now we need to give equations of horizontal and vertical asymptotes for each function. So for function f, horizontal asymptote, let's recall that since the denominator is of the higher degree than the numerator, the equation of horizontal asymptote is just y equals 0, and the vertical asymptote comes from the points out of the domain of f. So at -1, therefore x equals -1 is a vertical asymptote. Now for function g, let's start with horizontal asymptote. This time the numerator and denominator are of the same degree, Therefore, we're looking at leading coefficients, which are -1/1. So the horizontal asymptote is y equals -1. The vertical asymptote comes from the point that makes the denominator 0. That means 0. So it's x equals 0. Observe that the horizontal asymptote of the original function is the same as vertical asymptote of the inverse function, and the other way around. Vertical asymptote of the original function is the same as horizontal asymptote of the inverse function. So basically, if you know asymptotes for one function, you can easily convert them to asymptotes of the inverse function. In the following exercise, we'll learn how to find a formula for the inverse function f to the -1 of x to the given function f. So if we have a given function f, it's a linear function 2x minus 3. How do we find its inverse? First, we rewrite the equation by replacing f of x by y, and then we're trying to solve this equation for x, making sure that x is on one side and everything else to the other. So the next step would be bring the 3 over and then divide by 2. So y plus 3 over 2. That's already the inverse relation. We start with y, we end up with x. So it reverses the process. However, we would like to write this statement in a function form. Therefore, the next step would be to replace x, but f to the -1 of y, because that's a function of y. Okay, we already have the formula for inverse function. Quite often, though, we would like to see the formula in terms of x, not in terms of y. So at that moment, please rename the variable y into variable x, because for a function it doesn't matter how you call the variable. Therefore, we can always rewrite this in terms of x. So the replacement of letters happens at the very end. I prefer if you will solve for x first and then interchange x and y, rather than otherwise. Because imagine if those are not x's and y's, and let's say we deal with a function that refers to some word problem. For example, it could be like c and t. C could stand for cost, t for time. If you start interchanging t and c, at the end you may not know what stands for what, and your cost will be t and your time will be c, which wouldn't make sense. So it's too much confusion. I found it a lot better to just solve it in terms of x all the way along, and if you need to change the variable, you can do it at the very end. Sometimes, especially in word problems, it's not really desired to rename the variable into different letter. Okay, let's try this strategy on the second example. So what we need to do first is to rewrite it with no function notation, just expression, and solve this expression for x. Well, the x appears in the top and in the bottom, two different levels and two places. What we need to do is to bring x's to the numerator. So the first step that I would suggest is to multiply the whole expression by its denominator. That will give us y times x minus 2 equals 3x plus 1. Then, since we want to solve for x, open the bracket, multiply through, so it's xy minus 2y. Then we want to collect terms with x, bring them to one side. And if they will be on one side, we can already factor the x, because it becomes common factor for these two underlined terms. So take the x out, and then we have y minus 3 equals 1 plus 2y. Finally, solve it for x, that means divide by the bracket to the other side. So we end up with this expression. This is already our inverse function. We just need to replace x back to the f to the -1 of y, because it's a function of y. And if you want to see it in different letters, because we're so used to expressing a function in terms of x, we can finally give the answer as f to the -1 of x, just by renaming y into the x. So that's our final inverse function. Remember that at the end you should have the same letter on both sides. So for example, if you write f to the minus 1 of y, the expression should be in terms of y. If you write f to the minus 1 of x, the expression should be in x. These two expressions are exactly the same. They are just written in different letters, but they represent the same function. And we have one more function to find the inverse formula. Well, let's follow the same rule. This will be y equals x squared minus 2x. And I want to solve for x. Solve for x. So, how do I do that? Since this is x squared and this is single x, the only way to do it is by completing the square. So let's complete the square of this part. X minus half of the middle coefficient, which is just 1, square it, but that gives me the first two terms and also the third term plus 1. Since I didn't have this plus 1, I need to subtract that one. Okay, now I have x in one place and I need to solve for it. So let's bring the 1 over. There will be 1 plus y equals x minus 1 squared. And now to reach the x by itself, I need to apply square root on both sides. But now remember that square root of something square is actually absolute value of this something. And then it would be equal to square root of 1 plus y. However, we need to look for x, so we need to get rid of the absolute value. And at that moment, we need to use the condition that x's are smaller than 1. If they are smaller than 1, for example 0.9 minus 1, it becomes negative. So this expression is negative. To drop the absolute value, I need to use opposite to the expression, minus x minus 1 equals root of 1 plus y. So now to solve for x, let's bring the minus to the other side. So it's actually negative root of 1 plus y. And then add 1. So it's 1 minus root of 1 plus y. Good. Now to rewrite this as a function in terms of f to the minus 1 of x, this is the same as f to the minus 1 of y, which is here, right? But we want to rename the y in terms of x, so you have 1 minus root of 1 plus x. So that's our inverse function, providing that we have a restricted domain of x's smaller or equal than 1. To visualize the situation, let's graph the original function f. That was x squared minus 2x. Well, it's easy to factor this formula into x times x minus 2, so it's very easy to see the roots. One root is 0, the other root is 2. And it's a standard shape of parabola with leading coefficient 1. So the vertex is at the midpoint. We can use this midpoint. We can evaluate f of 1 very quickly. This is 1 minus 2, so it's negative 1. Yes, it works like this. And standard parabola means 1 across 1 up, 2 across 4 up. So that's our function. But we are taking this function only for x is smaller than 1. That means we are taking only this branch of the graph in order to take the inverse, because if we restrict the domain from 0 to 1, then this part of the graph is invertible. It's monotonic, therefore it's invertible. Okay, let's draw the diagonal and see the shape after flipping over the diagonal. I will draw it in blue. So this point 1, negative 1 becomes negative 1, 1. The point 0, 0 is still there. And the point negative 1, 3 becomes 3, negative 1. So we need to connect these three blue points. That will be somehow like this. Okay, so the blue shape is an inverse of the red shape, and notice that the blue shape is 1 minus root of 1 plus x, because we have the upside down root, that because of this minus. The original root is moved one step to the left, that's why the vertex starts from negative 1. and it's also moved one step up. That's why it starts from the y value 1. So yes, that's our function f to the minus 1, with the original being f of x here, this red part. Okay, the next question checks our understanding of what inverse function really tells us. Suppose that function f of x represents the number of cars that can be built for x dollars. So x is in dollars, f of x is number of cars. This whole thing is number of cars. What does f to the minus 1 of 1,000 represent? Well, that was f, and this is f to the minus 1. So if f takes dollars, the cost, and attach to it the number of cars, that's our f of x, then the f to the minus 1 is taking number of cars and attach to it the cost of producing those cars. So f to the minus 1 of 1,000 really represents the cost of producing 1,000 cars. And the last application problem. A landscaping company uses the function, and here's our function c of x, to determine the amount in dollars it charges per tree to deliver and plant x palm trees. So this is a cost per one tree. However, this cost changes. If the order is, let's say, for more trees, the cost will be different than if we would order just single tree. Find c of 5 and interpret the meaning of this value. Well, that shouldn't be too difficult. C of 5 means that we need to plug it in 5 into the formula. But the important thing is to understand what is it that we are actually doing. So what the 5 stands for? Well, x represents the number of palm trees planted. So what is the cost per one tree if 5 trees were ordered to plant? C of 5 is 600 plus 140 times 5 over 5. And if we use calculator, we end up with 260. So again, the meaning of it is the cost of planting 5 trees is $260 per tree. That doesn't mean that we pay just $260. It's 260 times 5 trees, the overall cost for us. But if we order 5 trees to plant, they will charge us $260 per one tree. Now, the second part of the question asks us to find inverse function c to the minus 1 of 160 and then interpret the meaning of this value. So first, to find the inverse function, we can do it in two different ways. We can actually find out the inverse function in a general form and then evaluate at 160, or we could plug it in 160 for the c of x value and then solve it for x. So since c of x is 160, therefore we plug it in 160 on the left hand side, copy the rest, and solve it for x. Solve for x. Okay, let's multiply by x. Subtract 140, so we have 20x on the left hand side. This is 600. Divide by 20, we end up with 30. Okay, but then what does it mean? What does this 30 really means? Well, we need to order 30 trees to plant in order to pay just $160 per tree. That's what it really means.